I would like to welcome you all to our webinar on arc flash hazard reduction. The topic for today's webinar include ways to reduce arc flash hazards, how to use arc flash reduction in EasyPower, whether that's through coordination, maintenance mode operation on particular protector devices, and so on selective interlocking. We'll also look at some example systems and how you might, for typical systems, how you might reduce your arc flash energies. We will look at some design considerations, and we'll follow that up at the end with some arc flash hazard labeling comments. Ways to reduce your arc flash hazard. The first and foremost way to reduce your hazard and the energy that you'll be exposed to during energized work is to de-energize the work or the equipment and do all your work while there's no energy being supplied to it. It removes all hazards, and it's essentially a 0.0 calories per centimeter squared working environment. But that cannot always be done. So we're going to look at some ways that the incident energy at a particular piece of equipment can be reduced to improve worker safety. So there are three ways that are listed. The first is probably the easiest, but just by increasing your working distance, you can reduce the incident energy. It's not always practical, but it is something that can be done for certain work tasks. You can also reduce the fault current. This is probably more of a design issue when it comes to reducing fault current. You can reduce fault current by having smaller transformers instead of designing for 2500 kVA transformers. Maybe you add multiple transformers that are, for instance, 1000 kVA apiece. Your fault current will be lower in each for the smaller transformers. Other ways that you might reduce fault current is by adding impedance to the system through cabling or through, for instance, current limiting reactors. The method that we're going to discuss today has to do with more reduction of arc time. You can reduce the arc time through many ways, but within the software, the method that's used is basically adjusting trip device settings, putting in new trip devices with retrofitting your existing equipment, and then we'll also look at some of the trade-offs that are necessary. And when we talk about trade-offs, we're talking about protection versus coordination. It's sort of a balancing act. The twin goal of maximizing protection and maximizing coordination are often directly conflicting, and the protection engineer must strike a reasonable balance between the two. It's important prior to performing any coordination study or trying to reduce your arc flash hazards to completely understand the system that you're looking at, so that when you adjust settings to improve the protection, where the worker safety is the #1 factor, you're not overlooking other hazards that may exist. For instance, if you have a chemical plant or you're in a refinery and you have some process that by shutting down that area increases the hazard that people or workers or the community in general would be exposed to. You don't want to get stuck in that kind of predicament where you've overlapped these two criteria. So it's important to understand where you can improve your hazards, but through coordination, and other areas where selectivity or system reliability is more important. There may be, when we talk about a balancing between the two, maybe under normal operation, selectivity is a requirement, but during the maintenance or the energized work, the implementation of, for instance, equipment and protective devices with maintenance mode settings is a viable option, where a maintenance mode setting is activated just while the maintenance is being performed, and then once it is complete, your system is put back into your normal operation. Or maybe with zone selective interlocking or some other mode of protection, you can make the protection that you're looking for work for your situation. Typically, your system is an assortment of fuses, multi-case circuit breakers, whether they're insulated case or they could be insulated case, they could be motor circuit protector. The requirement of those breakers is that they have an instantaneous. Those fuses and multi-case circuit breakers are nice because if the fault current is high enough, they will trip instantaneously. Unfortunately, if the fault current is not at that point, then the amount of time it takes that breaker or protected device to trip significantly increases. Low voltage power circuit breakers with short solid state trips and protective relays have a lot more functionality as far as adjustments that can be made to increase the level of protection that's available. So the three main topics here as far as in EasyPower that we're going to discuss today are coordination, how you can use coordination to reduce your incident energy, and some of the ways that you may do that is, for instance, with relays. If you have electromechanical relays, you may try to reduce the amount of time between your relays and tighten up your time intervals. Sometimes in older systems, as the system has grown over time, the coordination is not always updated, and you may see areas that you can easily improve and reduce the trip time required for those devices. If you're looking at digital relays or retrofitting your mechanical relays, most digital relays have the ability to have multiple instantaneous functions, and you can use that to your advantage with instantaneous time delays to have lower trip times that coordinate better with your low voltage circuit breaker trip devices. And then as you get into the lower voltage systems with the LV PCBs, the low voltage power circuit breakers, enabling short time delay and using setting the I2T to on or off. Typically in the off state is where you see a lower incident energy, lower trip time, which results in the lower incident energy. So with that, we'll start and show a few different examples and how you would use these different things that we've just discussed within EasyPower. So I'm going to open up EasyPower. We're going to work through a few files. I'm assuming that everybody here that's a part of the audience has at least some level of understanding of arc flash and coordination. If you don't, you can follow along, and I'll try to explain a few things, but I'm doing it on the basis that you have a fundamental understanding of how to get around EasyPower. So the first example that I wanted to show is with low voltage fuses, and how changing out your low voltage fuses to a different type may improve your arc flash. This case here has lower energies, but there are points within your system where you might have something at 15 or 20 calories per centimeter squared that you want to reduce to a lower level, and maybe just changing the fuse to a different type of fuse, even though it's the same continuous current, may fix the issue that you're having. So I'm going to go into coordination focus, and I'm going to plot the TCC to show the difference here in the curves of the fuses. So you can see that the average melting time curve is for the JKS fuse. They're all, I've selected all Busman fuses for this example, but it's mostly about the type of fuse that I want you to take away from the example here. So this first, the average melting curve, the JKS, it's a J-type fuse. Typically, J-type fuses will clear quicker than RK1, which is the yellow curve, or RK5 fuses, which in this case is the orange curve. So if I select all the equipment and fault the buses, I've had to change the screen resolution and change a few things about the screen to allow the TCC to be shown better for the web meetings. So the screen might look slightly different than yours. So we're going to fault the bus, the three. Actually, we'll fault one bus at this point, and okay. So faulting the RK1, if I right-click on the curve and go to Insert Arcing Current tick mark, you will notice that, and I'm going to zoom in here so make sure that you can see it, but the arcing current for a fault at the panel is 4,434 amps. That means the fuse will clear in that amount of time. So I am going to, for demonstration's sake, insert a tick mark at this current. And I'm going to put it as an interrupting just so that it is up a little bit so I can move it around. So let's see if this, okay. So the fault current for a fault in any of the panels will be the same, the arcing fault current. So as you can see here, for a fault at panel 1, the incident energy is 0.3 calories per centimeter squared. That's because the trip time is around 0.02 seconds. Because this is an average melting time, there is an adder that's added in the arc flash analysis when deriving the trip time. So it's approximately 0.02 seconds, where for a fault at panel 3, which is the RK1 fuse, it'll trip in about 0.08 seconds, and then as you get into the FRS, which is the RK5, it's approximately 0.4 seconds to trip. And that's where you're getting the higher. So if you have higher energies that you want to reduce, this is, and your system is protected by fuses, the fuse is not too high. I would say 600 amps or less. You might be able to try it with some of the larger fuses, but and look at different manufacturers. But you're going to see this at the smaller fuse sizes. That was the first example. This next two examples, I'm going to show you the maintenance mode and the short or the ZSI function within EasyPower, and show you how those functions work and how they can be applied to your system. So we have a simple circuit here. It's definitely been just been put together to show what we need to show. So you might see some things that look a little different, but the important point is that these two GE breakers are set up to have maintenance mode settings, and then the relay is also set up to have maintenance mode setting. So I'm going to go into the breaker here for this feeder, and so the trip unit in this case is a GE IntelliGuard TU unit, and it doesn't matter if you're using a Siemens or a Square D or AC Pro. Those don't matter. It's all applied the same way. The terminology that's used, like GE uses RELT, everybody has their own terminology, but it's the same format. So in this case, we've set the, you would set your normal long time and short time settings as you would for normal operation, and then in this case we added the maintenance mode function. That's for the breaker. The main is set up the exact same way. You have the long time and short time settings, and then you also have the RELT setting. So cancel out of that, and then we'll go into the relay. And the relay I've got set up with a 5150 IEEE function and a 50 maintenance. This relay is a Schweitzer. It's a SEL 751A. But again, any major manufacturer supports a maintenance mode. They each do it slightly differently, but within the software, it's applied the same way. So going into the settings dialog, the function ID1 is the normal operation, and we have a tap setting and a curve setting, and then we also have the instantaneous. Under function ID2, we have the maintenance mode. So this maintenance mode has been set at 10 for now. So I am going to go to back into coordination focus, and we'll start by plotting. I'm just going to plot the feeder breaker with the feed to the panel board 1 in this in this example, and I'm going to plot that. So the curve that's showing right now is for your normal operation. If you right-click on the breaker in the one line, I'm going to turn on the maintenance mode. Now you'll see that there's a box that comes up and shows that the maintenance mode is on, and you can see that the maintenance mode, it was set for a instantaneous curve at 1.5 times the current pickup. So even though the short time settings are still there, this overrides it from that setup. If the instantaneous was set higher, then the short time would be seen a little bit more. So if I take this off, I'm going to turn it off. So when you're normally running your system, there's no maintenance being performed. This is your system protection. If I was to fault this bus, so I'm going to double click on the. Before I do that, I'm going to make sure we are in Arc Flash. Okay, double click on the bus. I'm going to right click, show the arcing current. So under normal operation, it takes approximately 0.15 seconds for the SST to clear the or the breaker to clear the fault. As you can see, the instant energy is 11.9 calories per centimeter squared. If I right-click on the breaker, so now this is from the standpoint of your electrician or your maintenance person going out to do whatever the task is, they would turn on the maintenance switch, and that would activate the maintenance mode. And you can see that once the maintenance mode has been activated, it reduces to 3.4 calories per centimeter squared. Let me turn this one off, and I'm going to close the TCC. So similarly, you can do that for the main. Plot the TCC, different curve. It's selective with the feeder curves, and you can fault the bus and show the arc flash result. And I need to make one change here. I'm going to go into the short circuit options, and I want to show the including main result. So I'm going to go to plot TCC again. So if I fault the bus, show arc flash. So for this case, it takes approximately 2.3 seconds. So that gives us an extreme danger. So this is for equipment downstream of the main breaker, where the main breaker is protecting that equipment. So again, if you right click, turn on, now it's 4.2. So that would be any equipment downstream of the main breaker. So for any fault at the main breaker, the upstream relay would be clearing that fault. So I'm going to turn this off again, and go to short circuit options. I want to show the excluding main result, and we'll plot that down through the relay through the main breaker. So I'm going to go plot TCC. So here's our relay under normal operation. Show arc flash again. So at the main breaker, it's 357 calories per centimeter squared. If we reduce that, or insert the arcing tick mark, it is almost 4 seconds for the relay to clear that fault. If we right-click on the relay, similarly to the way we did it with the maintenance or with the low voltage breakers, you can see that the incident energy is reduced to 6.6 calories per centimeter squared. The relay works slightly differently as far as in the TCC. I have not shown that to plot. So if you click on the plot TCC button, it now shows. And so you can see that it's going to clear instantaneously. So it's an instantaneous trip plus the breaker opening time is the clearing time for this, which reduces that instant energy. So you can see that by implementing maintenance mode, you can see some significant changes to your arc flash incident energies. The one thing with the maintenance mode is you have to make sure that once it's enabled, that once the work is done, that the system is, or the maintenance mode is disabled, and you go back to your normal operation settings. Otherwise, if you leave your settings, your system coordination will be limited. In this case, where for the relay, the maintenance mode is well below your transformer inrush. So if you ever tried to start a transformer, you would have issues from that perspective. Also, you may have a lower level fault that gets passed up to other protected devices, and you get devices tripping that you're not expecting. So that is one thing that needs to be watched. Okay, so that's maintenance mode. So I'm going to close this and open up another file here that we'll talk about ZSI a little bit. So there again, this example shows some square D devices that have that, but all manufacturers have it. So if it's something that you're looking at, you can talk to whoever your distribution person is that you typically work with and see what they have as far as the function equipment with that function. So the main idea behind the ZSI is that if you have a fault, say for example at panel board 2, BL2 would be your tripping device, and since it's the closest device, you want it to trip the fastest. So ZSI will trip this instantaneously. Now, and panel board 1 would work the same way with breaker BL3. Now, so for a fault at switchgear, the bus switchgear 1, BL1 under normal settings is set to be selective with BL2. But if the fault occurs at switchgear 1, we may not want it to take that long to trip. So the thing with ZSI is when a fault occurs, there's communication between the devices And if BL1 finds out that the fault is occurring upstream of either breaker BL3 or BL2, then because of that communication, the trip time can be reduced. So zone selective interlocking allows breakers to distinguish different fault zones and trip more quickly. If a breaker picks up for the fault current, it sends a signal to the so for example, if this breaker trips, or I'm sorry, if this breaker picks up, it sends a signal to the BL1 breaker saying that I'm going to trip for this fault. Any breaker that would receive that signal will not trip instantaneously. And then in the case of BL1, if it picks up, but it doesn't receive the signal from BL2, for instance, for the fault on switchgear 1, then it would trip instantaneously. So to set this up, I'm going to open the dialog here. Actually, I'm going to go into coordination focus prior to opening the dialog so that we can see the temporary change. So I'm going to plot all three and make a TCC. So BL3, BL2, it's this curve. They have the exact same settings. BL1 is the main. So you can see under normal operation, the settings are selective. Now if I go into the dialog, we have a tab for ZSI. And so right now the ZSI is disabled as shown here, but we have entered that the breaker BL2 is dependent on BL1, which is upstream. Now BL1, when you look at that one, it doesn't have an upstream breaker. So currently the ZSI function is off. So right-clicking, I'm going to turn the ZSI on. Now for these devices, it's a STZSI is the function. There's other devices that have instantaneous ZSI and ground, depending on the type of device and the manufacturer that's selected. But I'm showing this one today because it's a little simpler to understand in a short time period. So if we right-click on that and set the ZSI on, I've highlighted which devices are there. So if I, for instance, let's do a arcing, make sure we show our arcing current. Okay, so if I fault this bus, we have our ZSI on, you can see that this, with ZSI on, this becomes the curve. And because it didn't get a signal, there wasn't a signal that was sent, this is the new curve. So it'll clear much quicker than under normal operation, or if the ZSI function was not enabled. Similarly, if I was to fault the switchgear 1 bus, you can see that BL3 and BL2 are still in their normal state, but since a signal was not sent to the BL1 function, it reduced to that lower level as well. And so the arc flash incident energy is 4.1. If I was to take the ZSI function off, so I'm going to say yes. So if the ZSI function was not enabled in this case, the fault incident energy at switchgear 1 would be 25. And since it's been enabled, and we'll say yes, it's 4.1. So this is another method that you can see some real improvement in your arc flash incident energy calculations and the energies that are present within your facility. So that'll finish the discussion on the ZSI. So I'm going to close this file and open another one, and it's a file that I've created from some systems that we've worked with in the past as far as reducing the arc flash incident energy within a setting, within a system. So this is taken from this is a small portion of a real-world facility, and their objective within this facility was to their main goal was to get everything below 40 calories per centimeter squared for normal operation. And then where applicable, because of the cost, to apply some maintenance mode or equipment with maintenance mode options. So for this substation, the original breakers were Westinghouse DB breakers with Amtector 1A trip units. Depending on the device, they either were long time and short time, long time, short time, and instantaneous, or some were actually long time and instantaneous. So if I go through and fault these 3 MCC buses, so I'm going to go into short circuit focus, and I'm going to fault the 3 buses. So you can see, based on the existing settings, and need to bring up the arc flash hazard report. So turn that on in the options. So we're looking at a number of different trip times. The relay MCC E2, that was the one we just looked at. It has an instantaneous, but it doesn't appear to be tripping on the instantaneous. MCCA is tripping instantaneously, and then it takes a really long time for MCCB1 to trip. So this may be a common case within your facility. So what you might look at doing, and every system is different, so you need to be sure that before you implement any of this that you're aware of all the different possibilities and what effects it may have on your system. Even though this is a real case, every case is different and needs to be looked at that way. But some of the fundamentals and the thought process that we've used can be applied. So if we go through each, we'll start with these, and I'm going to take a couple notes here quickly. So now, since we know the instant energies are a wide range. I'm going to go back into coordination focus and we'll just work with each one individually. So plot the TCC for this device. So in this TCC, we have the main on the MCC has a fuse and it's a fuse breaker, and they may have applied the fuse differently. It may be a feeder fuse the way that they have applied it. But if we fault, but that's not important as far as the arc flash. If you're trying to coordinate against it, then this becomes more important. So if I'm going to fault show arc flash, and I'm going to fault MCCE. So it's at 33 calories per centimeter squared. Now, when you look at this, our fault current is that the upstream trip device sees is 1800 or just over 18,000 amps. So there's a couple options depending on as far as how you can adjust these settings. And I'm not worried about, for this example, about the long time or long time delay, or even short time pickup. If I want to reduce the time, now they show a couple relay breakers here, but you may have to look downstream at your feeders to make sure of your coordination. But from an arc flash standpoint, by just reducing the short time delay from 0.05 in this case to 0.33, I just reduced the instant energy to 21.8 calories per centimeter squared. If I go down to the next level, it reduces it to 11.9. You may say that's good for your case as far as the level that you need to reduce the instant energy below. Now, depending on your philosophy and how well you want to reduce your instant energy, you also, in this case, because this trip unit has an instantaneous trip function, you can also look at starting to reduce the instantaneous. So if you drop it to 8, which is 12,800 amps, now our trip time has reduced to approximately 0.05 seconds, which gives you an instant energy of 3.3 calories per centimeter squared. So from where we started at 33 calories per centimeter squared, we've reduced quite a ways. So, but you also have to consider what effects reducing that instantaneous has on the rest of your circuit, because you are reducing your reliability, and that's where we talk about those special cases. So that's one case. If we go, I'm just going to show this one, even though we won't be changing any settings because the hazard is small. But this is an LI function. So if I show arc flash and we go look at our trip, that's the instant energy. The LSI is set at 7 point, or the instantaneous on the LSI is set at 7.5. For coordination, you may want to increase that, but that doesn't affect your arc flash. The third case that is shown here, this one, I'm going to delete this motor. but this one had the highest incident energy, and it was like 311. And that was due to the fact that this also is an LI function, and it's set at 12. And if we show the arc flash, show the arcing current, you see it takes almost 15 seconds for that to clear. I think it was 14 something. But that's why you get the 311. And this one, if I reduce the setting to about 7, I can reduce the incident energy to 1.3 calories. Where, in the other case where you had the LSI function, you may not want to reduce the instant energy, or the instantaneous to reduce the instant energy further, because you might be at a level that you're okay with, and you don't want to make the trade-off of the reduced system selectivity. Where in this case, by reducing that setting, you reduce the instant energy much more. So this may be one case where you do it, where the other one isn't, just because reducing your instant energy from a really, really high number to something that's very low may be a trade-off that you're willing to do. Now, in this case, this facility decided that they would change out main breakers, the trip unit on the main breakers, with AC Pro utility relay AC Pro, retrofit these, and add a maintenance mode if necessary. And then they also changed out their old electromechanical relays with new digital relays, so for the main purpose of the maintenance mode. So in this case, I'm going to make one change before I go into. I'm going to change this to excluding main for one purpose, and I'll show you in a minute. So actually, I'm only going to plot. I don't want to plot all those motors and clutter up the TCC too much. But okay, so right here, the settings that on the main, this is the main, the pink curve. The others are all the feeders. So there appears to be fairly good selectivity with those at this point. So if we go into this, actually in this case, even though the device does have a maintenance mode setting, in this case it may not be necessary to enable that. Now, if you look here, we have 19.7 calories. That's for normal operation, so it's clearing in about 0.25 seconds for a fault downstream of the main breaker on this switchgear bus. Now, I'm going to show the arcing current. You can see that the arcing current is right here, and one of the reasons they changed this to an AC Pro is because the settings with the existing Amtector 1A were much higher. The settings that had to be set required almost 0.5 seconds. So by just changing the curve or the device to get a different curve, it allowed slightly better settings, which we were able to reduce the instant energy by half. So sometimes maintenance mode may not be what you're looking for. You may change out a device just for a different, or a trip unit for just a different trip function, or different curve type. Now, in this case, if I was to put in a quick trip unit, and let's see what we got here. So we'll put it right above the, actually we can, let's put it at 6, and you'll see right now by putting it at 6 it didn't change that, but so we're going to have to reduce it a little bit more. So let's go to 5. We'll just hit apply. Still not quite there, so 4, go down to 4. Okay, so by implementing the maintenance mode, and it has an instantaneous, it's down here, it's covered by the other devices, but it'll reduce it to 3.9 calories. So this is just to say that sometimes, even though you put in a device that has a maintenance mode setting, you may not, the risk of people not putting it back to the normal state may not be at that level. So the last couple things, as far as in this example, to briefly mention are with the relays. Now, there's 2 different examples as far as the relay. This relay here is feeding this transformer. This relay here is really protecting the cable because each of the transformers is protected by a fuse. So they have different, the settings are based on different fundamentals, because in this case you want to make sure for selectivity during normal operation that this relay is set to be selective with each of these, where it doesn't matter if this relay, if you have a fault at this switch gear, if this breaker trips, this fuse trips, or this relay trips first. It may be nice to have a little bit of time delay between each, so you know where the fault occurred from a trying to fix it standpoint. But from an arc flash standpoint, you just want it to get cleared as fast as possible to reduce the hazard and the exposure to the qualified worker. So in this case, you don't necessarily have to be completely selective between each of these devices. So I'm going to turn the maintenance mode off of this one, and I'm going to plot plot this section here. So you'll notice here that, and I'm going to just delete these cables so they're out of the way. If we fault on the secondary, actually, I have to change one thing in the options before we go further. Change it back to excluding main, because that's what we're worried about now. Go to actually pull up the TCC. So if we fault this bus and do arc flash, and I'm not sure which device is going to clear this, but I think it's this one. So it takes approximately 1.3 seconds for the fuse to clear this. This is if we're selective. The fuse was chosen based on the transformer size, so there is some miscoordination between the main, but in reality we're not too worried about that. So one option you have, since this is the clearing time, or the I'm sorry, the arcing current, we can add with this digital device a instantaneous setting. I'm going to set it at where our tap setting is at 400, so I'm going to set it at about 600 amps, which is going to be about 15. And I'm going to have a time delay added to that, and I'm just going to put it at 0.3 for right now. So it looks like I need to move that up a little bit for the instantaneous, so I'm going to put it at 20. So you can see that, and I'm going to zoom into this area a little bit so we can get a better look at that. So 16 is a little high, or 20, I'm sorry, 20, the setting of 20 was a little high, but let's just try 16. Still, it's miscoordinated with this. I'm trying to just get it off that curve. Okay, so it's just off the curve. We need to have a time delay. This is about 0.25. You need to have it for coordination purposes. Like about a tenth of a second between that. So I'm going to set it at 0.35. Now, in this area, there's a little bit of, it's a little bit less as well. So maybe you want to go up a little higher. Maybe we go to 0.4. This is where understanding what we're doing and what kind of selectivity. This is the main breaker, so I really don't care that this is selective. So maybe I do go back to 0.35. Also, if I don't care about selectivity and I care about arc flash, maybe I don't worry about this, and maybe I should be coordinating this based on the downstream breaker. So based on that setting, you can see that just by adding that instantaneous and time delay, I've reduced my instant energy to 34.2 calories per centimeter squared. And if I need to change my arcing current, so now, as you can see here, so that's where it's going. So that's what's nice about the TCC. You can tell where your currents are and how you can need to adjust your curves to see what the different hazards will do for you. So in this case, I've significantly reduced my instant energy with just changing the settings in the relay. If you have a electromechanical, you may be able just to use the, if I was to get rid of the instantaneous here and treat it more of just a 51 function relay. So disable that, say OK. You know, you might be able to get it down to where the fuse is, and maybe you could, you know, depending on what other stuff you have downstream, you may be able to find something, or if you have a different curve. There may be some options, especially as you get into smaller transformers where you don't have to come down quite as far to get the lower trip time. But in this case, we can also add in the maintenance mode settings similarly to the example we did earlier. So we have the arcing tick mark there. I'm going to right-click and turn on the maintenance mode. So with the maintenance mode being on, so plot that. So the maintenance mode's been set way down. I don't know if that's a realistic setting, but as long as it's below this, usually since we're dealing with safety, I'll rather be a little bit further away from the arcing current because it's still, you know, it's a probability as far as how that number has been come up, or how that number's been derived. So So I like to add a little bit of safety on the maintenance mode setting. And so the best in this system as far as a fault on with the relay protecting it in the maintenance mode is 11.8. So with the time delay, it was 19.8 calories per centimeter squared. So, depending on at what PPE level, you change over. If, say, you only went up to 8 calories, you may not care to enable a maintenance mode setting in this case. I know I'm gone a little long here. I just have a couple more things to mention regarding this this relay here. Under normal operation, the fault current at each of these, or I'm sorry, the incident energy at each of these equipment. Let's fault these. One was 107, this one's 54, this one's 1.2. So the fuse here does a good job, but it's only a 600 kVA transformer. These two are 1500 kVA transformers, and these fuses do not provide good arc flash protection from an incident energy standpoint. So one thing that this facility considered was because under normal operation, this needs to be selective for reliability purposes, but they still wanted this to be lower if energized work did need to be occur. Here they had a number of switchgear that had a main breaker protection, but they also had a number that had fuse protection, and the fuses did not help with their arc flash. So this 54.6 passed through the whole switchgear, and so if they needed to operate these or get into the switchgear, they needed a way to get it below 40 calories. So their choice was to enable a maintenance mode setting that allowed all the transformers to be energized and be fully running, but did not or they did not, let me start over. They wanted all the transformers to be running, but when maintenance needed to happen, they needed to be lowered. So the maintenance mode was set so based on the full load amps of all the transformers, but was set low enough that it would apply, the maintenance mode setting would apply to the estimated arcing current at each of these equipment. So just for to show this, I'm going to plot this TCC. So you can see that this is selective with this fuse, but if we fault this bus, and we'd show arc flash. So the full load amps for all the transformers was about 166 amps at the 12.47 kV. But if we fault, or if we show where the arcing current is here, 492 was the maximum that could be set at for the maintenance mode. So if we go to the maintenance mode, so 300 is what it's set at. I'm going to go over here and enable the maintenance mode setting, and then I need to plot that. So you can see that with the maintenance mode setting, it dropped it to 8.6 calories per centimeter squared, and the with the instantaneous trip, which significantly reduced it from the 54. The other switchgear was reduced as well. But they also know that it does come with additional risk that if during that fault or during that maintenance, when the relay is in maintenance mode, if they have a fault on this switchgear while they're working and this relay does trip, it's taking off a larger portion of their system. So, so that's where when I specified at the beginning that you need to understand what your main goal is when it comes to this protection. That's very important. So that will wrap up the examples. I got probably another 3 or 4 minutes to go to wrap up with labeling and a couple design comments. So right, the label that's shown here is our standard label for above 40 calories based on the 2012 standard, which is trying to do away with the PPE levels. But a couple comments on that. When you do have maintenance mode versus like a case where like the zone selective interlocking, where when zone selective interlocking is present, that is always enabled. So the arc flash incident energy is always lower, will always be lower. You don't have to enable anything. So putting a label out that has that lower incident energy is probably okay. But when you get into a maintenance mode setting, there's a lot of different opinions on how this should be labeled. Should we put a label out for normal operation and then another with what it is under maintenance mode? Should we put a label out and then put a note with the maintenance mode incident energy? So in this case, the label that we're looking at, if this was the normal operation, this would be the label, and then at the bottom of the label there would be a note that says if the maintenance mode is enabled, you can put or have the lower incident energy there, so like 6 calories per centimeter squared, and a different PPE the different PPE level that is there. But that's all part of the training for your workers and deciding which case works best. And then also the other case would be to put a label like this. That's the worst case, and then use the work permit process to reduce it and to allow the user to have a lower or reduce the amount of PPE that needs to be worn. So the final thing is just a little bit of comment regarding system design and arc flash. What we've talked about today can be applied to new systems, but it also in a lot of cases is for retrofits as well, or trying to reduce the arc flash in an existing system that's already been developed, and you're just trying to reduce it. There are some fundamental things that can be done during the design process, so either a new facility or if you're adding a substation. When you're talking about arc flash incident energies, doing it up front can really help reduce those hazards. Versus from adding breakers and relays to your medium voltage system, or breakers to your low voltage system. It all, some of it you don't have much choice with, but other times you can. one of the things that we talked about at the beginning as far as the main factors that affect the incident energy are working distance, fault time, the amount of time it takes for it to trip, and then the fault current. Well, anytime you can put in a smaller kVA transformer or substation, that's always going to reduce your fault current. So that will give you lower incident energies. A high resistance grounding reduces ground fault energy and potential escalation to a three-phase fault. That doesn't necessarily mean that you're going to have lower incident energies because the arc flash calculations are all based on three-phase faults. But in this case, the likelihood that a fault is escalated or a line to ground fault is escalated is reduced, therefore improving your arc flash. As far as some other things that you can look at, differential protection anywhere. We didn't discuss that, but that will reduce the amount of time it takes to trip within that differential zone where you don't have to be coordinated with overcurrent devices. That can significantly reduce the incident energy. Zone interlocking, like we discussed, you can do it 480 volt or medium voltage. Current limiting fuses and breakers, anything that will get a faster trip. Arc resistant gear in the medium voltage systems. As long as the doors are closed, once you open a door, then it loses that arc resistance. But those are things that you can consider. Moving equipment, protective equipment outside of the actual switchgear room. Smart relays, when you, actually I'll slide forward to the next. So this was the slide for the one that we just talked about, and I'm actually on the next slide. Smart relays, so that if you walk into a room, you automatically enable those maintenance mode settings or a second group of settings that reduce the hazard around the equipment that people are in the proximity of. Pressure light sensitive devices to detect arc flash and trip. Another thing that can, you're not having to coordinate within the system. If it sees a trip, it goes instantaneously. And then transfer trip, if you have a trip on a fault on a 480 volt side, you can transfer trip to other places. All kinds of things with that. So with that, that's the end of the presentation today. I thank you for attending, and sorry that it did go a little longer than anticipated, but I hope that you gained some insight into and some application as far as reducing arc flash that you can use within your own systems or in your own designs, or if somebody else is helping you out with that, you're able to follow what you've been told easier. So with that, that'll be the end of the session, and thank you for attending.